work, and hopefully you'll feel much better after I ask the TAs to turn on the air conditioner. Can we turn on the middle one? All right, so we turn on everything we have. Okay, it's better to turn on everything you have. You don't have to save the electricity from the department. They have wasted too much. Okay, we cannot save the department just by saving the electricity bill here. All right, okay, these are the other examples, which are a little bit more complicated. 5 variables. Okay, as you can see, we list all the residue here after we do the decomposition. Okay, the decomposition is based on the Shannon expansion theory. All right, so it's almost the same. So what we're interested in, how do we use this residue map to come up with a circuit design? So after you know the theory, you do the decomposition. But according to my experience, all right, I have been teaching this course for 30 years. So all the students, as far as I understand, none, besides during the exam, none of all the students I taught before use this kind of expansion. Everybody follow the example I gave in the early of this lecture. And an example that I gave yesterday, okay, step number 1, find out the pull-down network, and then use a dual to develop the pull-up, and so on and so forth, and then change the size. Anyway, I just let you know there are other ways to do that. We call all of these ways are systematic design methodologies, and they are based on the Shannon expansion and the residue map, and they are all called tree networks. So after we finish this, we'll take a break, and we'll see you 2 weeks from now. So please pay a little attention to what I'm going to say here. So tree networks, okay, this is very good for exams. You know what I'm saying? Okay, in the midterm exam, these are very good to torture students in the exam, because most of the students does not give a damn, okay, about what that is. A lot of students like the way better than I taught, okay, using the duality, this kind of thing. So how many different networks we have in the textbook or in the literature? At least 1, 2, 3, 4 ways. Okay, they are all based on the Shannon expansion theorem. So basic design method, okay, repeatedly apply Shannon's expansion theorem and use trivial literals. Okay, so here we see that free form and uniform. So just check the name. Free form means that you can do whatever you want. Okay, there is no rule for that. But for the uniform way, uniform tree, there is a special rule for that. Okay, but well, unfortunately, students don't like it. Okay. All right, let's go to the exam number 1. So see, look at these 2 pictures. Okay, and compare with the one over there, multiplexers. Check that. See, you see, is there anything similar or something common? Okay, the implementation of tree networks, okay, for arbitrary Boolean functions, basically the same. See that we have a block, a big block in the middle. Either this one or this one. Okay, this is using CMOS switches. And this one uses NMOS switches only. Okay, so this one apparently a little bit of more economy because it uses NMOS. And this one uses the transmission gate. Every switch is composed of 2 devices, N and P. So, and you check that here you have 0, 1, XX bar. So we have 4 different selections. Okay, you don't know how many lines you need, but at least you understand one thing. We need 4 selections. So you check these 4, which are similar that we have over here. See that? We have 1, 0, WW bar. 4 different options, selections. See, this one is also the same. So basically, you can consider that this is a different form of that kind of a multiplexer. That's all. Is that clear? So basically, these two ways are similar. Okay, this is the one you learned before when you are a freshman, and this is one you learn when now you are a senior or junior student. And what is the difference between these two? Okay, if you use the transmission gate as a switch, you don't need an inverter or buffer over here, because when you use the transmission gate, you are ensured to have VDD to ground full swing. So you don't have to bother to do this. Because if you use the NMOS switch as, only, that means you are going to have a voltage drop at the end of your pass. You will get at the most VDD minus VTH. So you got to have an inverter or buffer at the output to pull it back to VDD so that you have a full swing. So the difference of these two implementations are switches are different, outputs are different. Basically, all the selection method, they're identical. Okay, and the input selection lines are identical. 4 types, 0, 1, a variable, and a variable bar. That's all. Okay, these are the 3 networks. Understood? Okay, so it's quite easy to have a brief conclusion. So let's get to some example to see how it works out. Okay, right now this one is a demonstration for freeform tree implementation. So if you are given f function like this way, so step number 1 is similar to the one that I show you. Okay, reverse it. So we have a G, which is equal to F inverse, F bar. That is this way. We have how many variables we have? We have Wx, y, z for variables. Then the next step, okay, we use the channel expansion, okay, to decompose the original equation into this way. We decompose versus with respect to W. We have a W bar times the residue, W times residue, okay, respectively. Then we're going to do all the way down. This is number 1. I'm sorry, we're going to stop here. So check this out. In the first decomposition, we decomposed W, okay? And then we decomposed, okay, in the second level, X. And then it's decomposed to Y. All right? W, X, W, Y. So we can do it randomly. It's free. Okay, you can do whatever you like, as long as you can come up with a similar thing like this one. Okay, then we stop here. Okay, there is no rule to follow, so that's why it's called the freeform. All right? So you are going to, let me copy this one down, and then you'll see how it is going to be mapped with the circuit design over there. Okay, so hold on a second. Let me copy the equation over here. So this is a G. So after the 2-level decomposition, we have a W bar. Then big bracket, X bar. Okay, here's 1. And then I cannot remember it. I have to do it step by step. Y bar, Z bar. Okay, then this one. Okay, then the next bracket is W times, this is kind of silly, though, but it's fine, X, Z bar. Okay, then Y, Z. Okay, we stop here. Make sure I copy everything right, because I'm old, I'm over 60. Very soon I'm going to be qualified to buy the senior citizen tickets for high-speed rail. So see that we check everything is just fine? What is the purpose of this one? Because apparently in the first level of decomposition, we decompose versus W. But in the second level, okay, this guy deliberately decomposed the first term with respect to X, then the second term to Y. This is just for demonstration. In fact, nobody do this kind of stupid thing. Anyway, so you check this out. Basically, in the in the, in the center of every term, the final term here, check this out. It looks like something. It looks like the input. It looks like the input, okay? So check over here. Looks like an input. All right? So this is something got to be watched. Okay, WXY over here. So let's check the answer. And you have many ways to implement it. This is just one of them. Okay, I'm sorry, it's not over yet. Oh, all right. So see, it's not over yet. So we have to decompose to this way, see? To see this one. So we are going to see, because here we still have these guys. Then we decompose further to be a long one. This is very, very long. X, we need it. I have to copy it, excuse me, because it's quite important. Will you understand why we are going to do this way? Y bar, Z bar. Okay, hopefully I don't mess up with the duplication on the board. 1, 2, 3. 1, 2. Yeah. 1. Okay. And then W. Decompose, so Y versus Y, then X, then Z, then X, Z bar. Okay, this is a bracket, and Y of Z. That's it. All right? I think this is the end. When to stop? When you have only single variable left, okay, in this smallest bracket, parentheses, 1, 2, 1, 1, 0 bar, 0 here, 0 here, 0 bar. You cannot stop over there, because this is good, but these two are not. It's not over yet. So you have to go down to this formula, and this is residue. Residue, these are the residues over there. Okay, and after this one, what are we going to get? All right, so this is how to implementation. It's a free format. So how to check? Why we have to go down to the final residue? Because we like to have one selections, 1 0 Z bar or Z. That's why. Because we have to follow the general form that we see over here. We like to have this kind of stuff. And this is just a switch box or a multiplexer. So that's why. So we go down back to this one. Oh, now let's check. See that? So everything, there are 4 possible inputs. Either something is wrong here. This is, okay, this is correct. 0, 0, and this is 1. See? Okay, now let's check every term. So you see that the first term, 1, okay, and X bar and W bar. So where is it? This is a 1, right? Controlled by this transistor, and this transistor then goes to output. That's the first, for the first term, X bar and Y bar. That's this term, check. Over there, okay? Then you check the next pass, Z bar, YZ bar. Okay, this is the second term over here. Y bar, this is the inputs, the Y bar, X, W bar. Y bar, X, and W bar. See that? Okay. Well, this is the final answer. Of course, it's more neat. Okay, then the next term, 0. 0, Y, X, W bar. You check. 0, Y, X, W bar. Okay? And the next term is 0, 0, X bar, Y bar, W. 0, W bar, Y bar, W. X bar, Y bar, W. All right, and this is Z bar. It's over here. This one goes this one and over here. And this is the last term, Z, Y bar. Z, Y, and W, okay, over there. And that's the inverse, because G is the inverse of the original F. All right, then the next question you ask, how the hell I can come up with this kind of a circuit so well organized? Let me tell you one thing, it's impossible, because you are a beginner. So for the beginners, what you will do to make sure it's correct is this way. I'll show you how to do it, okay? That's a very pretty answer, brilliant. So if you derive this equation, what you will do, don't panic, don't worry. You just do it one by one. How to do that one by one? See that? We take the first term as example. This is what you do. This is X bar, and this is W bar. Okay, you work from the right-hand side to the left-hand side in order. That's one. And going to the output. And the second term, this is Z bar, right? Z bar, then you go to this way. the rightmost term is this way. W bar over here, then you have this one, Y bar. That is X. This is for the second term, okay? Go over there to the end, don't worry. Number 3 terms, 0 goes through Y, never mind, goes through Y or X, that's fine. Because the order is not irrelevant. And this is X, and then you go to the W bar. Okay? You do it step by step. How many paths you need? 1, 2, 3, 4, 5, 6. You have 6 paths. You just do it one by one. And it's a little bit more complicated, but I guarantee the functionality is good. That's all. Okay, and the end, you have a total of 6 inputs to map those 6 terms. Then in the end, okay, that's it. And the logic function is equivalent to that one. It's good. But what he did better is that they merged, okay, those common terms together. That's all. And this kind of merge needs what? Needs experience. You got to spend some time to work on it. Okay, so that's why it's called a free-form free-form network implementation. This is the most easy one, straightforward one. However, the size, the number of transistors is bigger. Another one is more neat. Okay, more compact. Okay, that's the difference. Basically, if you can derive the equation like this, okay, down to the last variable, then you can draw these circuits, no problem at all. It's ugly, it's not pretty, but the functionality is good. It works. All right. So this is free-form tree, and then of course the counterpart of free-form tree is uniform tree. Uniform tree is that, okay, by the same decomposition, but the circuit implementation is much well designed. So you check the equation over here. We have a G, which is the reverse of W. Then we decompose in sequence, okay, following the W, X, and then Y. That's it. So you see that? You found the W, the second level, the first level is a decomposed versus W. Then this one is versus X and X. And this is a difference. This is a difference from the previous one. The previous one, you see that in the second level, the first decomposition, the first term is versus X, and the second term is versus Y. That's why it's so complicated. Okay, and then the result is that they become a free form. But my advice for those beginners is that if you want to do that, to use the tree, it's better to follow this one. In the first decomposition, every decomposition, you just take one variable as your variable. That's all. So this is a W, and this is X. And the last one, this versus Y, versus Y, versus Y, and that's it. So because you have the W first, X, and the Y. So this kind of decomposition, you are going to get this kind of form. It's much, much better. So this is kind of random, and that one is much more organized. So in this way, if you follow the uniform tree decomposition, then you are going to get something like this one. You are going to get a big triangle. Big triangle, and this is the output. Okay, and the first variable that it decomposes is W. So W and W bar will come over and take over everything close to the output. And the second variable it decomposes is X. So the X and X bar will come over, take care of the middle part of the switch. And the last one is Y, because W, X, Y. So Y and Y bar will coming in to take over the control of this part of a transistor. Then you have four inputs, which are 1, 0, Z, and Z bar coming from this side. So it look at this way. You can consider this big triangle is a tree. Now let's check the answer. You're going to love it. So if you follow the uniform tree, you're going to get something like this. See that? It looks like a triangle, right? See? This is output, of course, got this one. So W and W bar will be in charge of the last two transistors close to the output. And in the middle, XX bar will consider this group. And Y and Y bar, the last one to be decomposed, will close to the input. And here you have 0 and 1 as an input. That's it. It's more organized and systematic way compared to the uniform tree. See, now you check all the paths over here. Let's check the first one. See that? Z bar goes through the Y bar control, X, and W bar. So W bar, X, Y bar will get a Z bar. Let's check the original equation. Where is it? It's here. See? 1, 2, 3. This input will go through 3 transistors respectively controlled by Y bar, X, and W bar. That's how it works. So you follow the uniform tree decomposition, basically come up with a big triangle or big tree over there. And it will look like this way. It's pretty and brilliant, very systematically. And the beauty is that it is a binary tree. If you rotate this circuit 90 degrees counterclockwise, you'll see that this one coming in, break into 2 parts, and here coming to break into 2 parts. You can break into 2 parts. So that basically can see this. This is output node. Okay. You have 2 paths. Okay. The first path, okay, controlled by W and W bar. Okay, over there. And this one is break into 2 paths. X and X bar. Okay, and the last term is over here. Y bar, Y bar, Y bar, Y. Okay, so if we draw this tree, this binary diagram, we just follow this equation. We can find out what the hell we need over here. So we need W bar, X bar, Y bar, we check that, okay? So we have a 1 go through here. Let's check. Y bar, W bar, X, Y bar. W bar, X, Y bar. So this is going to be Z. Check over here. See? And this is Y, X, W bar. Y, Y, X, W bar. So this is must be 0. This is bar. See? You plug in all the numbers over here in the leaf. So basically, the design based on this equation is a binary tree. It's a binary tree. Okay? You can rotate it by 90 degrees and you will see the tree, how it works. Okay? For example, the Y, X, or see that Y, X, W. So that this is past, W, X, Y. So this one is the last one. This is Z. Over here. For those terms who does not show up, 1, 2, 3, 4, 5, 6, 7. So at least one term is missing in the leaf. That's fine. So this is called the root and the leaves. All right. So basically, uniform tree is a binary tree. So every decomposed variable is used to in charge of one layer of transistors. Okay. This is a uniform tree. Very pretty and lovely. And then there are other trees. Okay, 0, 1, X, X bar tree. Okay, they are similar. Okay, they are similar. Of course, that we still have to count down the channel expansion theory. And a lot of mathematics symbols, okay, students hate it. Never mind, I hate it too. All right? So literals X bar and constant 0 to 1, so it's the same. We have 4 input possibilities, with 4 input options. Okay, it's 1. So these are the equations. If they have everything, must be 1. If never, there will be no intersection, so must be empty set. So the definition of f s over y is a set of any combinations of y such that r of x equal to s. And s is one of the elements in this set, 0, 1, x, x bar. Okay, basically the same. Okay, it stands for the input set. All right? So, see, it looks almost the same. See that? And we have 4 paths over here. We have 4 possible inputs, 0, 1, x, x bar. It's the same over here. And the difference is of these 2 diagrams is that this is controlled by a transmission gate. And these are based on the N switch. So it needs to add an inverter or buffer at the output. Okay, and we have 4 paths over here. This is deliberately for 0, this is for 1, this is for x, and this is for y x bar. Oh, let's check how it works out. All right, so this is based on the residue map. And this is a given equation, yz, xz, xy. Okay, this is equation. Then you plug in GC multiplexer. So this is a residue map. Right now, if we use YZ as a selection line, and X is the input, okay, input selections. So 0, 1, 2, 3, 4, 5, 6, 7. So this is not K map. Please keep this in mind. This is residue map. Okay, don't mess up. And when you see those mean terms, you make a circle. Okay, and then, as I say, all the residues are written over here so that you don't mess up. So there is no circle, the output is 0. We have 2 circles here, we got 1. And these 2 columns, they are mapped to 0 and 1, so the input got to be X. So basically, if we don't want to use this one, that's fine. We can use the multiplexer. Right? We have two input line to select one of the fours. 0, x, 0, 1, 2, 3. Then we, all we need is to couple 0, 1, x to the inputs. That's it. And this is the multiplexer. And in this textbook, okay, it's slightly complicated. It uses this is a stupid way to do that. Well, it's not stupid. It's some way that student doesn't like. For example, we want to generate a 0. What is the 0 term over here? X bar and Z bar. Okay, the 0 term is over here. So the control line here is 0, 0. So it has to be 0, Y bar and Z bar to control two transistors. So when both of these are high, then X will be, Y input will be coupled to F because they are selected. Then in the next term, you see that 0, 1, when Y is 0 bar, Z is 1 high. So this is this term. Y and Z bar, this is one of them. The other one is the other way opposite. Here, Y bar and Z. These two passes are for these two. And the last one is Y and Z. Okay, so Y and Z are in charge of this pass, going to the output, and this is 1. So that's it. You can either implement the user way in the textbook, use this as 0, 1, x bar 3, or use the multiplexer. It's up to you. Both way works. Okay, and in terms of the number of transistors, of course, this one is better because it use 8 transistors. That's all. But if you use the multiplexer, it'll be larger. It'll be larger. All right. So this is the the 0, 1, x bar 3. So it's pretty easy to understand what the hell is going on. Okay, then we move on to something bigger. Okay. Well, Jesus Christ, this is too complicated. Well, we have an f function that big, then we do the inverse. Okay, before we go to do any manipulation, we will inverse it and use a g. Then we have these mean terms. We have 3 here, and it stands for these mean terms. And then the next step is that, okay, we follow the similar steps. We derive the residue map over there. Okay, so, and then you are already familiar with residue map. And this one is kind of odd, okay? You see that? You see W, X, Y. And then you check the number here, it's kind of weird. 0, 0, 0, 0. This is 0, right? 0, 0, 0, 1 is over here. So 0, 1, 2, 3, 4, 5, 6, 7. Okay, that's another way to implement it. Okay, of course you can do this way. And this example is just a typical example to show you different implementation. If you decide to select the variables you wanted to decompose, that will give you totally different residue map. And the question you ask is, how the hell I can understand which one is the optimal solution? The answer is, I don't know, because you have to keep trying. But as a beginner, or for the beginners, okay, my strong advice is that you just follow the simple way. You work from left to right, okay, because you are not pursue the best or the optimal design. So what you need to do is that you come up with a design which can function properly. That's good enough. That's good enough. Okay, so this kind of artwork, okay, it's a very special design. So the way that it decomposes is 0, 1, 2, 3, 4, up and down. Of course, that, okay, we follow the same idea of a residue map. We can have the similar circuits over here. So for the, excuse me, for the 0, we're going to have W bar. W bar, let's check. Okay, see, 0 here, W bar, XY. W bar, XY. And for the another term, W, X bar, Y bar. See, that's for the zero inputs. For the zero inputs. For the one input, how many terms we have? These two terms, 0, 0, 0, 0, 0, 1. So it got to be W bar, X bar, Y bar, and these two terms. And then we can merge them together because we have something in common. So we just use the mathematical way to find out the common term. So we are going to eliminate Y bar to Y using the basic Boolean manipulation. And for the Z, how many terms do we have? We have these two terms, 101, 101. And this one is 111 over here. Again, we use a Boolean, basic Boolean manipulation. We just take X bar and X away. We merge them together to become this one. And the last one is Z bar. We have this term and that one. So these are the two terms. And we can combine them together similarly to have X bar, right, this one. Okay? So basically, we have path number 1 for 0 input, path number 2 for 1 input, path number 3 for Z, number 4 for Z bar. So if we don't check the answer, we can directly come out with a circuits which will function but not pretty, which will be look like this way. We gotta finish this one as soon as possible. Okay, so right now we have these 4 equations. So let's check it out. The first one here, we have 1, 2, 3. Okay, 1, 2, 3 over there. Okay, it cannot be merged. So we have these two. What the hell is that? It's a W bar, this is W. And then XY. X, Y, X bar, Y bar. And their inputs are both the same, that is 0. And the output are the same, goes to something to be ready. All right, then check the next term. Next term is much more easier. We have only 2 variables because the Y is gone. So the next one is X bar or W bar, X bar over here. And this one is coupled to 1. So this one come over here, and this one go all the way over there to be ready for the output. The number 4 is for Z. How many variables do we need? We need a W and Y. So Y is over here. Okay, this is Z. This is W, and that is Y. This is Y. The last is, I'm sorry, the last is X, so there is nothing over here. Z bar, go to the X. So this is X and Y bar. And this one is G. And then we need an inverter to become an F. All right, so it's not done yet. It's not done yet. This is W bar, W bar, W. Okay, beware that you need the variable and its complement. So this is in charge by W, in charge by X and X bar, and in charge by Y. That's how you do it. Okay, mine is not that pretty. Let's check the answer on the textbook. It's much better. Oops. Okay. Now, let's see what the difference is, okay? Now, this is the implementation in the textbook. W, X, and Y. All right? Okay? How do we calculate the performance? Let's check. Basically, you got to check two things. How many transistors you need, and what is the longest path? Longest path stands for the longest delay. So let's count the number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A total of 12 transistors in addition to the inverter. How much I need? 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. Same. The same. Okay? And I also use an inverter over there. See? And it's ugly, but that one is better. All right? So my conclusion is that if you can derive the equation, then you should have no trouble to come up with the circuit design. So what is the value of an engineer? Over here. This is what the value is. You know the drill, and you know how to implement it using the mathematical way. That is why I keep telling all the students in electrical engineering department, based on the experience that I have, math, okay, logic, are the fundamental of every field of engineer. If you are good in fundamental things, you will be no trouble to switch field. So a lot of your seniors tell you, okay, which field is much better, which one is much juicy, okay. Don't feel be attracted or terrified, okay. You don't need that. All you need is to take care of your basics, mathematics, engineering mathematics, electronics, microwaves, all right, circuit theory. Then you can go to any field you like, all right. So what the value is here. This is where the value is. From the equation, build a table, derive the equation, then follow the equation. You can get the circuit, even though that's ugly, but it's working. Understood? Yeah, that's pretty easy. Don't be traumatized or threatened, okay? It's not hard. I'll tell you a story, okay? My major, when I was in graduate school, okay, at the beginning of my graduate study, I selected communication. Okay, communications. Well, I was good in math, but the thing is, I failed when I studied in the USA University. I failed in the PhD qualifier. Okay, in the area that I was proud of, communication engineering. They only passed 3 students, and I was number 4. So what do you do? You cry like a baby, okay? You go on the street and make a protest, what? Or use the internet to complain everything about the school. The exam was not fair, okay? And the professors bloody called the bastards, something like that. We never did that. Okay, I just changed my field. In the next year, I select computer engineering and I pass. That's it. Another field I passed is digital signal processing. Okay, I was not traumatized. I was not afraid. Of course, I feel frustrated because I worked so hard and I was this close to pass. In the field that I think I'm really good at, but the thing is, a fail is a fail. So in the next year, I changed my major subject to computer engineering. And however, importantly, all the trainings I learned in communications about mathematics, okay, helped me a lot through the last 30 years in my research. Because without strong, or at least a solid mathematics theoretical background, it's so hard to compete with other researchers in this field. So it's the same to the engineers, okay? If you can hold on to your study in those basics of electrical engineering, electronics, microelectronics, circuit design, circuit theory, okay, EM waves, microwaves, okay, all the students hate that. Control systems, engineering mathematics, and trust me, you will be the loved ones of any company in the research and development department. All right. So I'm not sure whether you understand what I'm talking about. Okay. Don't give it up. Okay. Denzel Washington, the guy, the very famous movie star, he had a great speech. Okay. In the ceremony, he said, "For those young men, if you want to fall forward, not backward." Do you understand what he's saying? He said, if the young man wants to fall, okay, fall forward, not backward. I'm 60, you are only 20. Fall forward. Okay, backward. Okay, what he said, that's a very inspiring speech, that one of the most inspiring speeches that I've ever heard. He encouraged those young graduates, okay, your life never starts, okay, unless you start trying. Don't be afraid to fail. Don't be afraid to fail, okay? If you if you are afraid of fail, that means you have not started even trying yet, okay? So he said, if you want to fall fine. Fall forward, because you're trying and you fall. And don't try to find another way to get out. Find an easier way out. Fall backwards. Very, very inspiring speech. Okay. So if you go to the YouTube, you can search that, Denzel Washington, and find out his famous speech. I love that one. Okay, I don't know how or who prepared the speech for him. That's very inspiring. Okay, so let's go to the last one in this talk. It's a 0-1 tree network. So we check the them over there. See, all the tree network we describe, we have 4 variables: 1, 2, 3, 4, right? 0, 1, x bar, or 0, z bar. Okay, so these are 4 possibilities. But in this 0, 1 tree format, it does not have x bar or z bar, this kind of thing. So this is called the 0, 1 tree, or 0, 1 tree. 0, 1 tree, that is quite easy. It's even easier. We only have 2 inputs. It's either high or either low. That's it. See, if you go back and check the previous tree network, how many inputs are there? 4 types. High, low, z bar, or high, low, x bar. But for the 0, 1 tree, we want to save students a lot of trouble. Okay, we only give you 2 inputs. That's either high or either low. There is nothing in between. Okay, so in this case, this general form looks like what we have talked about at the beginning of the lecture: pull up and pull down. See that? This is pull up. This is pull down. Pull up and pull down, the same. Okay, and then outputs, okay, the output is sitting in the middle of these 2 networks, and this stands for the low. And if you use, okay, the NMOS as a switch in these 2 blocks, then you gotta use what? An inverter here to pull up. For example, if you use an NMOS switch here, then you have a voltage drop, VDD minus VATH. Then you gotta need an inverter or a buffer to pull up the output voltage to VDD. So this is used to restore the voltage level. All right, don't forget this part. So this is 1. So what is that? How do we do that? Okay, it's quite easy. It's easier than the previous 4 value network. There's only 2 value. So apparently you like it. So basically it's the same. This is F, right? So F, then you inverse it to become F bar. We call it G. Then we become W bar, X and YZ. See that? All right? So, and then G bar equal to this one. This is what? we use De Morgan's law from here to here. De Morgan's law. This is W bar becomes W, N becomes R becomes N to become this way. Okay? So basically, it is almost the same as the approach I taught at the very beginning. So you check this one. This is W bar X over here. And then this is a term Y and Z over here. So these are the two terms, for two paths for the G. And then in the meantime, we like to generate the path for the 0. So the path for the 0 is the inverse of this one, which is exactly as the same, the F. So that is W plus X bar. W, X bar. See that? This is these two terms. And N. So they must be in series. Y bar and Z bar, they are in parallel. Then this is the pull-down network. Then both of them go to the same node, and this is the output. Then we use the inverter to pull up the output voltage. That's it. Easy peasy. And this is one exactly, well, not exactly, very similar to what I taught at the beginning of this lecture. Okay, pull up network, pull down. See? No trouble at all, right? So we have talked about the 4 types of four variable networks: uniform, freeform, okay, and 0, 1, X bar, okay, and this one, okay, 0, 1. A total of 4 types of networks. And it is my belief, as I said, none of the students will use it because you don't like it. It's too complicated. Okay, I think most of you like the one that I talked about at the beginning. But the thing is, very likely I will give this kind of thing in your exam. Okay, so it's better for you to understand how to derive it, right? Because in the midterm, we gotta have an exam. In the final, we need the exam. Okay, that's required by the university. So understood? So this is a 0, 1, a tree network. All right? Okay? One last slide, then we close today's lecture, the last one. This is the problem of Shannon's expansion. All right? Okay, now, a lot of students come up with crazy idea, but it's nice to have wild thinking. Okay, I encourage the students to have different idea, but I gotta warn you, when you apply this kind of tree network, you gotta be very, very careful. Okay, sometimes you mess up, and this is some example. Some of the examples that students make mistakes before. Okay, what's wrong with it? If you look at the format of this kind of network, tree network, it looks similar to those we just described, right? Okay, we have input from left. We have a lot of transistor worked as a switch. Then we have output. But the thing is, there is common mistake made by students is that, okay, hold on a second. Let's check this one. See, you cannot use a signal as an input and a control simultaneously. That's a basic rule. Let me repeat again. You cannot use the same signal to serve as input and control simultaneously. If you do that, I guarantee you 90% you'll make mistake. Let me tell you why. You check the number 1 over here. See that? X bar is the input over here, right? Then X is the control over here, right? So according to these circuits, hold on a second. I'll show you why this is messed. This is messed up. Let me redraw it over here and explain to you. So this is a very common network. Okay, if you do this way, if you X bar, and this is Y bar, No problem at all. Y used as input, X used as control. Everybody's happy. Okay, the only problem is that whether this function is exactly the thing you like. Okay, X works as a control, this is input, that's fine. But the thing, that example, it's not the case. X, Y, then, here we go. You have a 1 over here, this is X bar. Then you have the above equation F. F equal to 1 times X bar over here, and this one X and Y. Over there. See that? Okay, clear? Right, good. So what the problem is, if you follow the equation here, it seems fine. But the thing is, if you check these circuits, what happened? What happened is, if, I don't have the red. Let me use the red. Yeah, we have the red over here. Okay, I'll tell you what the disaster is. Okay, this is 1, right? Now let's assume X equal to 1. So what happened here? You have a 0. Right? Then in this case, this is 1, Y is allowed to pass. 1 is over here, 0 is allowed to pass. We have a 0 here. What if Y equal to 1? What's it going to get? You have a 1 coming over here, 1 here. You have a 0 from the top. You have a 1 from the bottom. Then you have something you don't know in the between. That's bad. See, this is Y over here. You have a 1, 1 over here. Then you have unknown. So why does that happen? Why does that happen? Because you use X as a control and the input simultaneously. Is that good? All right, let's check the next example. See that? Shit happens again. X bar control the transistor on the top, but X is used as input in the bottom. Then you're going to get this disaster over here. What happened? When X is 0, this is 1, right? So this is 1, 1 is allowed to pass over here, sitting here. Then Y is 1, this is 0, 0 comes in. Then you have a 1 and a 0 over here. Then what happened to F? You got nothing. You got unknown. So that's it. All right? Got it? And this one, check this one. This one, see? X used as a control variable. So this is 0, this is 1, this is 0. So Y is allowed to pass. Okay, no matter Y is high or low, it doesn't matter. So the only problem we have to worry is that when X is 0, then Y will be passed. But in this case, this is 0. I don't care what Y is. It's not allowed to pass. So it's guaranteed to be 1. So it works just fine. So as you can see, all the variables, you got to classify them into 2 types. You want them to be control, use them as a control. You want them to be the input, use them as an input. Don't mix them together. That's a basic rule. Understood? Otherwise, it will guarantee you will screw up. Okay, that's the last slide. The TAs are here. They can't wait to go home. So any question? Okay, thank you for coming. We will continue our class 2 weeks from now. All right, close.